They can be a little bit tricky to remember, so you guys might want to make flashcards and quiz yourself, because we have formulas on angles and segments in this unit. And some of the pictures look very, very similar, so that's why it can be confusing to mix up the equations or formulas sometimes. So again, color coding is going to be helpful, so if you like doing that, continue doing that. So we have already defined these two terms. These are a review, and then we're going to have a new one. So a chord, we talked about that on day 3. A chord is a segment whose endpoints are on the circle, so it means it's fully inside. So if you guys want to draw an illustration, right, that's a chord. Right, it's just some random segment inside a circle, completely inside. We talked about a tangent on day 2. That is a line or segment that skims right across the circle and it touches it once. So that's an illustration of a tangent. Now we're going to be learning about a third line called a secant. A secant is a line or segment that intersects a circle twice. A line or segment that intersects a circle twice. And so it's related to the tangent and the fact that it does cross through the circle and keep going. Right, so a tangent, right, it touches the circle once, but it continues on both sides. A secant is like that, where it touches the circle and it keeps going, but it looks like this. Right, it doesn't just touch the circle once, it touches it twice. So it's kind of like a slicing through the circle. A secant's interesting because it actually has a chord with it. It's basically a chord that keeps going. Right? This is a chord because it's completely inside the circle. It doesn't keep going outside the circle. A secant is a chord that has an extension on both sides. It cuts right through the circle and it keeps going both above and below as it cuts through.
If it was cut straight down the middle, we're going to do that.
What do you mean down, like through the center? It would still be a secant. As long as it goes through the circle and touches the circle twice, it's considered a secant. Whether it goes through the middle or right near the top or the bottom, doesn't matter. As long as it touches the circle twice and keeps going, it's a secant. Okay, so then we have a couple different theorems that we're going to be working with. We're going to talk about angles first. So the front side of the page is going to be more theorems and rules about angles, and then on the other side of the page is going to be segments. So theorem number 1, the measure of an angle formed by two lines or segments intersecting inside a circle. So you're going to see two theorems, one's for inside, one's for outside. So if your segments, and I'm going to draw the little dot here, if your segments are intersecting inside of the circle, you have a special rule that we're going to use. So if they intersect inside the circle, the angle is, I'm on the wrong side. What am I doing? Sorry, it wasn't my language. Okay. Half the sum of the, I use intercepted here. Yep, intercepted arcs. And to review what that word means in a second, finish writing this first. The angle is half the sum of the intercepted arcs. Sorry, that's plural. Remember I defined intercepted for you? I think it was either last lesson or the one before. Intercepted is the arc that's in between the arms of the angle. So I know you guys can't see it in color, but I highlighted them. One's blue and one's purple. So these two arcs here are what are created by the openings of the angle that you're using here. And so the formula is it's half the sum. But if you want to write that, you can write it like this. That's your sum. That's your formula, essentially. We have it written in words, and then this is your formula kind of format of that. So the angle is equal to the big arc plus the small arc divided by 2. You're going to have 2 arcs. Now, when I have these segments in here, and they could be lines too, they can keep going. Do you guys see how I've chopped the circle into 4 arcs, actually? 1, 2, 3, 4. You guys see that? How are you supposed to tell which of the 4 arcs to use?
They're across from each other.
They're across from each other, but so are these. So how do you know which arcs to use? Remember, this is the angle that we're working with here.
Oh, from the angle has to be.
Use the angle to help you figure it out. All right. Okay, they have to be in line with the angle. So if you think about a line or somebody looking through the angle, that's how you know which two arcs to use. If you try to use these two, those are not aligned with the angle you're looking for. So that's what can be confusing about that formula, is knowing which arcs to use. Typically they only give you the two that you need, but in case they give you all four, the two that you need are the ones that are lined up with the angle, not the ones that are going against it. You need them to all go in the same direction. Alright, so that's theorem number 1. Then we're going to learn theorem number 2 and then apply them. Some questions underneath to practice. This time, the measure of an angle formed by two lines or segments intersecting outside a circle. So like I said, we're doing inside and outside. So theorem number 1 is for when it's inside, and then all of these are outside. But we have 3 different scenarios of where it can be outside, unfortunately. Alright, so it doesn't matter which one of these 3 scenarios it is, as long as it's outside, the angle is equal to half the difference of the intercepted arcs. Half the difference of the intercepted arcs. Do you guys remember what difference means? Subtraction. So when it's inside of a circle, you use addition. When it's outside of a circle, you use subtraction. But otherwise, the formula is the same. Okay? So over here, you have the angle would be big minus small divided by 2. If it's inside, it would be big plus small divided by 2. If it's outside, it would be big minus small divided by 2. Alright, and the big and the small are referring to the relative sizes of the arcs. So you can visually see which one's smaller and which one's bigger. Clearly this arc is bigger and this one's smaller. So in this kind of scenario, if you guys have two secants that are intersecting out here, you would do this arc minus this arc divided by 2 to find the angle. Okay? If you guys had 2 tangents, remember the clown hat rule? What do I know about the tangents?
They're the same.
The tangents are the same, but if I'm not looking for the tangent and I'm looking for the angle instead, you would do the big arc minus the small arc divided by 2 to get the angle, right? And then if you have one secant and one tangent, sorry, this is a secant, that's a tangent, you would still do big minus small divided by 2 to get the angle, okay? So just remember what the pictures look like. Remember the difference between when you add and when you subtract, but they both divide by 2, right? So it's relatively simple, you just have to be able to recognize which one to use based on the picture. So let's go ahead and take a look. Okay? Go get some water if you need. Alright, so take a look at this one. The first thing I want you guys to think about is whether it's inside or outside. Take a look. Look at where the 2 lines are intersecting. Are they intersecting inside or outside? Outside. Okay. To get the muscle memory of the formulas, I want you guys to handwrite the formulas and then we'll plug everything in. So the angle equals, when it's outside, what is the formula?
Big minus small.
Big minus small divided by 2. So I'm going to handwrite the formula and then we're going to plug in everything we know into the formula and solve for what we're missing. So do I know what the angle is?
No.
Yes, I do. Right here. Okay, so 20 goes here where the angle belongs. That's why I'm having you handwrite the formula so you know where everything goes. The formula involves the angle and the 2 arcs. So the angle goes here, where the 20 is. What's the big arc? 70. The bigger arc is right here visually, so I have 70. What's the smaller arc? Nope. Y. Smaller arc is right here, guys. Look, use your eyes, okay? Bigger arc, smaller arc, right there. And then you're dividing that by 2. So again, once you know what the formula is, you plug everything in, and then we solve. How would I algebraically solve? Multiply by 2. Gives me this. Okay, so that gives me divide by negative, because you always want y to be positive, right? So you do that, you divide by the negatives to get them to cancel out, and you should just get 30. Okay, so that's how you would solve this kind of question. It just takes knowing what the formula is, plugging the numbers in, and using algebra. Alright, what about this one? Is this in or out? Okay, so what's the formula? Angle, always write the angle first. Angle equals what? Big minus small divided by 2. Now let's plug everything in. What's the angle? X. What's the big arc? What's the small arc? And dividing that by 2. So this one you can just do the 160 minus 92, find what that is, divided by 2, and you get your angle.
That's equal to
34. It's minimalized algebra when you guys are just looking for the angle, but when you know the angle and you're kind of solving backwards from one of the arcs, it takes a few more steps algebraically, but it's not necessarily complicated. Alright, what about this one? In or out? This one's inside, so what would the formula be for the inside?
Big plus angle.
Angle equals big plus small divided by 2. So let's plug everything in. What's the angle? X. What's the bigger arc? What's the smaller one? And then I'm dividing that by 2. So again, this is another straightforward one where you can just find what 165 plus 55 is, and then divide it by 2. 110. Alright, what about this one? In or out? So my formula would be angle equals big minus small divided by 2. It's subtraction when it's outside, addition when it's inside. Alright, so what's the angle? 30. What's the bigger of the two arcs? X. What's the smaller? And then you're going to divide that by 2. So this is another one where we have to do some algebra to get there, a couple steps. So what would I do first? Multiply the 2, zero the fraction. Oops, sorry. And then what? Add 150. Okay? So as long as you know the formula, the difference between when it's add, subtract, and you handwrite the formula out first and plug everything in, you guys will be perfectly safe. Just make sure you know how to do your algebra. Okay? Now, before we move on to the segments, I want to summarize everything that we've learned about angles. We've talked about 4 different scenarios with angles inside of circles. The first one, what happens if the vertex, and I'll draw a little picture above, right? What happens when the vertex of your angle is at the circle? How would you solve? Right, correct. It is a central angle. So how would you solve for it though? What's our little rule? So the angle equals the arc. That's our rule. If the vertex of the angle is on the center, it's coming from the center, it's a central angle, the angle is equal to the arc. What about when it's on the circle? That means inscribed. That's what we call these angles. It's inscribed. And your picture would look like this. Right? The vertex is on the circle. It's half. Well, the angle is half the arc. That's what we learned last lesson. So you have the central is equal to the arc, and inscribed is half of the arc. So those are our first 2 angles that we just talked about. This was day 1. This was day 4. Yeah, day 4. Right? These are what we just talked about today. If the vertex of the angle you're creating is outside the circle, what's our formula? So that would look, this is just one example. You could have any one of those 3 that I have drawn above. But if your vertex is outside the circle, what's our formula? Yes, angle equals big minus small divided by 2. And if instead, our 4th one that we talked about, if they are inside the circle, not necessarily at the center, but if the vertex of the angle you're looking for is in somewhere inside the circle, not the center, what's the formula for that? Yeah, angle equals big plus small divided by 2. So those are our 4 angle relationships from this unit that you need to remember. And it's all where the vertex of the angle is. Right, so that's an important little box. You can use that to study to remember all the different relationships that we're going to be working with. You have your visual, you have your description of the special names if they have one, and then the formulas. This is a good way to summarize and study that information. Now, the last information that you guys will be held responsible for is now how to solve for segments. And we have 3 new ones. These are the ones that are a little bit odd, a little bit trickier to remember.
I wish it was comic.
This one's not, this one's not. This one's pretty easy. These ones can be a little bit fuzzy. Alright, so we're going to have chords, tangents, and secants. It depends on what you're working with in this picture. So theorem 3 is when you only have chords. You only have chords. So this says when 2 chords are intersecting, right, the products of the chord segments are congruent. This is a worded definition of the theorem. The products of the chord segments are congruent. Now, what this means, and I've drawn this little picture, I have a blue chord and I have a purple chord. What this is saying is that the 2 segments of the purple chord, if you multiply those together, it'll be the same as the 2 segments of the blue chord multiplied together. So essentially the formula would be A times B is equal to D times C. That's what it's saying. You chopped up the chord into pieces. If you glue them back together using multiplication, if you multiply these 2 together and multiply those 2 together, they should be the same value. Okay? And just hold on to that. We'll see examples underneath where I can illustrate that. But just hold on to that thought until we get there. So again, it's saying that if you glue the pieces back together with multiplication, they should be the same for both chords. Alright, this next one is when you have 2 secants. So those are the lines that touch the circle twice. They cross right through, they slice through the circle and touch it twice. When you have 2 of those secants that intersect outside of a circle, that's really your only option. You can't have secants that meet inside of a circle. So they're going to be secants. So when 2 secants intersect outside of the circle, to get this wording right, the products, again, lots of multiplication, the products of the full, in all caps, full secants and their outer segment are congruent. The products of the full secants and their outer segment are congruent. Okay, so we're doing product again. So this is multiplication. What are the things we're multiplying? The things that we're multiplying are the full secant length and the outer segment of the secant. So the formula goes like this. I have 2 secants, right? The blue and the purple. How would I express the full length of the blue?
WX?
No.
W plus X?
W plus X. So the full secant for the blue is W plus X. What's the outer segment?
X.
X. So if I do the full segment times the outside part, so full times outside, all of the secant times just the outside part, that's going to be equal to, if I do that the exact same way for the purple one. What's the full length of the purple secant?
Y plus C.
And what's the outside part?
C.
Okay, that's the formula. So if you do the full length of one secant times the outside part, it's going to be equal to the full length of the other secant times its outside part. Some people like to call it, what's the abbreviation they use? It's like, I can't remember. They use like an acronym or something to help people remember. It doesn't really resonate with me. But it's the whole times the outside equals the whole times the outside. I think it's something like that. Whole times exterior equals whole times exterior. Something like, I don't remember. But Just try to remember it as the full length times the outside equals the full length times the outside, and that's how you would approach that kind of question. Again, just hold on to those in your brain, and then we'll see how they apply down here, and then they'll start making more sense. But before we get there, let's talk about our last one here, theorem number 5. Okay? So theorem number 3 was when we have 2 chords. Theorem number 4 is when we have 2 secants. This one is when you have 1 secant, 1 tangent. 1 secant, 1 tangent. In this picture over here, which one is the secant?
The one that goes to
Color.
purple.
Okay. The purple one is the secant, right? Which one's the tangent? The blue one. The blue one only touches the circle once. That's why it's a tangent. This purple one is the secant because it touches the circle twice. So make sure you know which one's the tangent, which one's the secant, because that's important for the formula. When a secant and tangent intersect outside of a circle, the tangent squared equals the product of the full secant and its outside segment. The tangent squared equals the product of the full secant and its outside segment. So the way that we work with the secant is exactly the same as what we just did. The secant, you should do the entire length of the secant times the outside. But whenever you have a tangent, you square it. We're technically doing the same thing as the full times the outside for the tangent, but because the tangent's full length and the outside segment are the same, you're doing t times t, which is t squared. So our formula here, the tangent is represented with a t. If you square the tangent, that should be equal to the full length of the secant times its outer segment. So anytime you guys are working with a secant, it should always be the full length times the outside part. It's the only thing that you're doing here is that you're now working with a secant and a tangent at the same time, and the tangent has to be squared. Alright, so I understand those three can be kind of complicated to remember. So we're going to take a look at a bunch of examples here, and then I have another entire page of practice with the angles and the segments mixed together, so you guys can see how those might look. So we're going to see a lot of practice so we can get this nailed into our brains. Alright, let's take a look at this first one. First, we need to figure out which theorem actually applies. So what do I have? Do I have chords, secants, or a tangent and a secant? These are only chords. So am I going to be using theorem 3, 4, or 5?
3.
Okay. So that theorem says that the segments of the chords multiplied together should be equal. So here's one chord. What would it look like if I multiplied those together? Well, how do you usually write that? 4x. So if I multiply those two pieces together, that would be 4 times x, so I call it 4x. And then what happens if I multiply the pieces of this together? You'd have the 6 and the 2 multiplied is 12, right? So 4x is equal to 12. What's x? 3. That's really all that is. The theorem 3 application is not tricky. That one's usually pretty straightforward. Okay? Alright, what about this one? Do I have 2 chords, 2 secants, or 1 secant and 1 tangent? 2 secants. So is that theorem 3, 4, or 5?
4.
Theorem 4. I know, they're numbered according to 1, 2 on the previous page, and then 3, 4, 5 for this page. Alright, so this one, when you guys have secants, you do the full length of the secant times the outside part equals the full length of the other secant times the outside part. So I'm going to color code them. What is the full length of that blue secant from bottom to top? What's the full length? Okay, what is 8 plus 6? Okay, so I'm going to write it out full hand just to understand what we're doing. So I'm going to do 8 plus 6, which is really 14, right? And then I would have to multiply that by the outside part. What's the outside part? 6. Alright, 6. Now you're going to do the exact same thing for the other secant. What is the full length of that secant? X plus 7. Remember, so you get full lengths of things that have been chopped up, you add them back together to get full lengths. And then what's the outside part? Okay, so now this is what I'm solving. I just simplified that algebraically. Alright, so what is 14 times 6? Okay? And then what would I do with this right here? Distribute. So this would be 7x plus 47, because you multiply the 7 times both of those. Now what?
C minus 49.
Okay, so I'm going to bring my work up here. Sorry, I kind of ran out of room. So what does that give you then? 35. So I don't show all the steps in my work. Is it 37?
84 minus 49 is 35.
Yeah, that's what I thought. Pretty sure it's 35. Okay? And then, so you move the 49 over with the 84, leaving you the 7x by itself. And then how do you solve for x from here? Divide by 7, so x is 5. Okay? That's that question worked out. Alright, what about the next one?
The same. Actually, there was no.
Is this 2 chords, 2 secants, or 1 secant and 1 tangent? 1 secant, 1 tangent. This right here is a tangent because it only touches the circle once. Okay? And then the other one is a secant. So for this one, you're going to square the tangent. And then anytime you have a secant, you do that whole times out type of thing. What's the whole length of that secant? 16 plus 8. And then what's the outside part? Okay, so now do 16 plus 8, whatever that is. And then multiply that times 8.
192.
192. So I'm here. Now how would I get z by itself? I don't want z squared, I want z.
Yeah, square.
Do it again.
Yeah, square root.
Square root. So I get here. Alright, now in this scenario I don't want decimals, so when we're working with square roots, we're going to simplify it. So again, think back to when we were in Unit 7 or when we were working with the distance formula with square roots. How would I simplify this?
16.
The biggest perfect square inside of 192, which is not 16. It's true that 16 goes in, but it's not the biggest one.
64.
64 is the biggest. It would be 64 times 3. 64 times 3 is the same thing as 192. Alright, if 64 is the perfect square, how do I actually write the simplified form?
8 square root.
8/3. So that would be my final answer for C. So anytime you guys are working with the tangent squared formula, if you get to a radical that can be simplified, you have to simplify it. Just like in any other scenario. Okay? See if you guys can do this one by yourself. Again, this is another one of the chord scenarios. See if you guys can do that one. Where you multiply the pieces together for each chord so it can be equal and solve for x. Alright, what do you get? 15. It should be 3 times x, or 3x, is equal to 9 times 5, which is 45. And you divide, you get 15. Again, that one's really, they can't make it tricky. In honors they can, but for your guys' level, they can't really make it beyond that level of difficulty. Okay, just multiply the piece. Don't try to multiply different pieces from different chords. They need to be on the same chord to multiply them together. Okay? Now, what about this one? It says 2 secants, 2 chords, or 1 secant and 1 tangent. 2 secants, because both of these lines here, segments, touch the circle twice. Alright, so again, you're going to do whole length times outside equals the whole length times the outside. So here's one secant right here. What is the full length of that? It is x. And what is the outside part? 3. So this would be 3x when you multiply it together. I know you guys are going to be tempted because you see an x and a 3, you're going to want to add them together. Don't do that. What does this bracket mean?
The whole thing.
The whole thing. Look for brackets and take them seriously. If they give you a bracket, they've already given you the whole length, so you don't add the 3 onto the x. The x is the whole thing by itself. The 3 is just the outside part. And then what about for the second? the full length?
250.
No, the full length would be the 10 plus the 5, which is 15. And then what was the outside part? Okay. So this is what you're going to be solving. So you have 3x, and then you're exactly right. The 10 plus the 5, the full length is 15. 15 times 5
75.
is 75. And then you would solve 25. Okay, so again, that's where you guys really need to pay attention in these questions with the bracket. You cannot be adding extra stuff on if they have the bracket. They put that there on purpose to show you what the full length is already. All right, what formula would I use for this one?
Theorem 5.
The one with the T, the R, and the S. Yep. We have one tangent and one secant. So how would I write the formula? Who can?
X squared
Okay.
equals 12 plus 4 times 4.
Yes. The tangent gets squared, so the tangent is the x, so you would square x. But then when it's a secant, when it touches a circle twice, that's when you add the pieces together to get the full length and multiply times the outside. So x squared is equal to 16 times 4, which is 64. What's the square root of 64? Because you're trying to get to x, so you take the square root. So x would be 8. Okay. What about this one? This is still theorem 5.
Yep.
How would I write the formula?
X squared equals 16 plus 2.
Okay, so the tangent is the x, so I would square that. Then for the secant, I would get the full length, which is adding those together, and then multiply that times the outside, which is just the 2. So x squared is equal to 18 times 2, 36. So what's the square root? 6. Sometimes the square roots are whole numbers, so you don't have to simplify the radical like we did with that 192. But if it is not a whole, perfect square, if it's not a perfect square, you do have to simplify. All right, what about for this one? What would my formula look like?
6 plus 4.
Not plus. The chords are multiplication. 6 times 4, which is, okay, so 24 would be equal to 3x. You multiply the pieces of the chords, and then you set them equal. So what would the value of x be? 8. And then our last one. You can tell me what the formula would be for that.
Theorem 4.
It is theorem 4. How would I apply theorem 4?
X plus 3. Plus 3 equals 7 plus 4.
Plus 4 times 4, is that what you said?
Yes,
Okay. So you get the full length of each secant and multiply it times the outside part. And then you work through it. So for this one, what would I do for the left side? Algebraically. Distribute. So 3x plus 9, because 3 times 3 is 9, not 6. And then over here you'd have 7 plus 4 is 11 times 4. 11 times 4, 44. And then algebraically you subtract the 9, divide by 3. Yeah, so let's round that to 1 decimal point. Let's round it, so it'd be 11.7. Okay? So that's your practice with your segments and your angles when you turn the page. I'm going to let you guys do this entire page individually, independently, okay? This has angles and segments mixed together, so you guys really have to keep your eyes peeled. Am I using an angle formula that we just learned on the first page, or am I working with the segments, which is just what we just finished working with? So I want you guys to go very carefully through this page. You guys can work with a shoulder partner if you need to. I'll walk around if you have any questions. But get through as much of this as you can, using the formulas as best as you can. I'll put the answers up for the first 6, so you guys can check as you're going. And then I'll scroll down and put the answers up for the bottom 6. Okay? So go ahead and start working on that. on the screen in case you're stuck.
Got it.